let's talk about VSEPR theory. VSEPR stands for Valence Shell Electron Pair Repulsion. And basically what this means is that any lone pairs of electrons are going to want to get as far away from each other as possible. So that's the quick and dirty explanation of it. Let's look at three molecules: methane, CH4, ammonia, NH3, and water, H2O. So the first thing we do is we draw their Lewis structures. Now this flat Lewis structure doesn't really tell me a lot about the three-dimensional shape of this molecule, right? Because I'm drawing something that's in 3 dimensions on a flat sheet of paper. So we need to use VSEPR theory to get a better idea of the three-dimensional shape of this molecule. So the way we do that is we look at the central atom, the molecule, the atom that's in the center of the molecule. So if we look at the central atom for CH4, we see that it has 4 bonds, and there are no lone pairs of electrons, correct? Whereas in NH3, there are 3 bonds, and there's 1 lone pair of electrons, and in water, there are 2 bonds, 2 lone pairs of electrons. So all we did is we looked at the central atom to make this conclusion. Now, based on that information, we can use the number of things on the central atom to diagnose its electron domain geometry, EDG. So in other words, you're looking at how many things are on the central atom. And by thing, I mean both a bond and a lone pair. So there are 4 things on the central atom. Therefore, its electron domain geometry is tetrahedral. There are 4 things on the central atom here as well, right? 3 bonds and 1 lone pair. So its EDG is tetrahedral. And then there are 4 things on the central atom here, right? 2 bonds and 2 lone pairs. So that's tetrahedral as well. So the tetrahedral, basically what this is like the parent shape, okay? Because the electron domain geometry includes both bonds and lone pairs. But in reality, a lone pair of electrons takes up a large amount of space, okay? Because these electrons are going to repulse everybody else. And so that's going to alter the 3-dimensional shape. So let's go back and diagnose the molecular geometry, which is the actual 3D shape. If your molecule contains no lone pairs at all, then your electron domain geometry and molecular geometry are always going to be the same. Now let's look at NH3, 3 bonds and 1 lone pair. So that EDG, that's the parent shape, but that lone pair, this lone pair right here, okay, it's going to occupy this space up here at the top, and it's going to push all these other bonds down. So instead of all of these being nice square, right, like what we're showing in our Lewis structure here, what actually happens is these are sticking down. And actually, these are sticking down too, right? This one's coming out of the plane towards you, and this one's going behind the paper. A little bit harder to represent on a flat sheet of paper, but that's what that wedge and that dash represents, coming out, going back. Coming out, going back. And then this lobe right here is taking up a large amount of space. And then in water, we have 2 bonds and 2 lone pairs. Okay, so 1 lone pair here, 1 lone pair here. So the molecular geometry for water is bent. We've got 1 hydrogen coming out of the page toward me. And so the 3-dimensional shape comes directly from the number of lone pairs, right? All 3 of these have the same electron domain geometry. They're all tetrahedral. So they all are based on the tetrahedral parent shape. But when we factor in those lone pairs, that's what gives us our final molecular geometry. 2 lone pairs gives us bent. 1 lone pair would give us trigonal pyramidal.